towards more secure networks. So this is kind of an outline of the presentation today. I'm going to give a kind of a brief introduction and motivation as to why we need this, or why do we use machine learning, particularly for this type of problems. And I'm going to discuss some of the works that we've worked at Western as part of the OC2 lab, in which we used different machine learning algorithms for different network security problems. So just before I start, I'm just going to provide a kind of a brief background about myself. I have a bachelor's degree in electrical engineering from the Lebanese Arabic University, followed by a master's degree in electrical engineering from King Abdullah University of Science and Technology. And I completed my PhD in electrical engineering from the University of Western Ontario in 2018. Currently, I'm a postdoctoral researcher and a sectional instructor at the rank assistant professor in the ECE department at Western. My research focuses mainly on machine learning and optimization modeling towards the management of next generation networks. A brief overview of the Optimized Computing and Communications Lab, which I'm a member of. The lab was founded in 2004 by Dr. Abdullah Shani. We currently have two postdoctoral researchers, including myself, 8 PhD students and 2 master's students. And the research areas that the group works on are mainly related to next generation networks, big data, data analytics, intelligent and automated systems. We have multiple collaborations with industrial partners such as Ericsson, IBM, Huawei, and many more. So if you want to get a kind of more information about the research group, you can check the link within the presentation. So to start off, we know that the internet has become an integral part of our lives, and as such, because of the fact that we have multiple devices currently connected to the internet, we are able to collect large amount of data. However, us as humans do not have the cognitive capacity to be able to process these amount of data. So to be able to make use of the data that's being collected and try to extract meaningful insights, one of the techniques that is being applied and gaining more popularity is the use of machine learning techniques. So in simple terms, machine learning allows computers to learn some patterns without being explicitly programmed. So they basically adapt and learn from the experience. The topic of machine learning has become an extremely popular topic within the development organizations that are looking to adopt data-driven approaches to improve their businesses by gaining useful information from the data that they collect. To illustrate this kind of trend of ML adoption, the recent estimate by Forbes, which was done in early 2020, estimated that the global market for the use of machine learning will reach approximately 42 billion Canadian dollars by the year 2024. Now, this was prior to the prior to the COVID pandemic. However, even with the pandemic, the adoption rates for machine learning have not significantly been impacted. Now, we know that these algorithms have been proposed in a variety of applications, such as spam filtering, house pricing prediction, healthcare systems, and whatnot. However, one of the main applications of interest in our case is network security. Now, the importance is the fact that many international companies have reported a large amount of cyber attacks, and accordingly, because of the data collected pertaining to these attacks, many of these companies have adopted machine learning or data-driven based solutions in order to prevent or detect such attacks. As an example, here we see that companies such as eBay, Facebook, LinkedIn, and Uber, all of them reported within the last 5 years having cyber attacks that resulted in between 50 and 145 million accounts being hacked. As a result of this, the Internet Crime Complaint Center estimated that the monetary damage resulting from cybercrime or cyber security threats rose from approximately 700 million Canadian dollars to roughly around $3.8 billion in 2018. So this shows the impact of or the strength and the amount of attacks, cyber attacks being initiated, as well as the corresponding monetary damage caused by these types of attacks. In this talk, I will focus on three kind of use cases in which we are proposing machine learning in order to detect these types of attacks, mainly in DNS type of squatting, in autonomous or connected vehicles, and in more generic network systems. So starting off with the DNS type of squatting case, we know that the DNS or the domain name system is the main protocol to translate between the IP address and the URL. So what happens is basically we have the name servers that contain these translation, and this is these files are typically saved per zone, and each zone provides a primary and secondary name server for resiliency, redundancy, and load balancing characteristics, basically. However, because of its naivety when it was originally developed, DNS lacks data integrity and origin authentication processes. This makes it prone to a variety of the attacks, such as denial of service attacks, registrar hacking, cache poisoning, man in the middle, and whatnot. However, one of the lesser known attacks which can have severe consequences is actually what we refer to as DNS type of squatting. So DNS type of squatting is basically registering a domain name that is extremely similar to that of an existing popular user or like a URL, with the goal of deceiving the user to go to the malicious website rather than the actual website. So for example here, rather than having PayPal, they would register a website called PayPal1. However, the character 1 and L might not be discernible when we put it as part of the URL. Now, the danger of this type of attack is that it can lead to the personal information being stolen, corporate secrets being threatened, or even committing fraud. So we need to have efficient and effective detection algorithms to detect this type of attack. Now, in general, there might be many potential methodologies, whether at the query level, the DNS query level itself, or the traffic level, depending on the nature of attack. In this case, because of the nature of the attack, we adopt a query level methodology using mainly supervised, like a mixture of supervised and unsupervised learning algorithms. So more specifically, the proposed methodology initially was to extract a set of representative features, applying some exploratory data analysis to get a better understanding of the behavior of the data, and then developing a majority voting based and simple classifier that's able to detect the DNS type of squatting attack. So as part of the exploratory data analysis process, we used a combination of graphical and quantitative data analysis techniques, mainly the histogram, which is more of a visual technique, and then the mean and standard deviation, which are more of a quantitative techniques, in order to get a better understanding of the behavior of the features. And we used 5 different types of supervised algorithms belonging to different types. So decision-based or key-based, neighbors are distance-based, logistic regression, and naive-based are more probabilistic-based classification algorithms. Finally, supporter machine are hyper-game-based. This proposal is to check the performance of different types of classification algorithms and the hopefully positive impact of combining these algorithms in order to reduce the variance and bias of the prediction. So to test our model, we used a combination data that contained a combination of just top 1 million domains and CryptoLockers list domains which were generated algorithmically. So CryptoLockers list domains generated algorithmically to be the malicious websites, and the Alexa's legitimate domains are considered to be the legitimate or normal websites. So the features that were extracted were 8 main features related to the domain name itself, because as we mentioned, the type of squatting attack is an attack by which the name or the URL itself is slightly changed. So what we did, we extracted 8 representative features related to the domain name length, number of unique characters, number of unique letters, number of unique numbers, and the ratios, in order, because these are representative of the domain name itself. So as part of the exploratory analysis, we noticed that the malicious websites or the websites that were algorithmically generated tended to have a higher distribution. So the distribution was not normal, rather it was more distinct, as well as having a larger mean and standard deviation, which makes sense because there are two main ways in order to generate modifications or variants of a legitimate website, either replacing a character or adding an additional 1 or 2 characters. That's why we notice that for malicious websites, they tend to have a wider distribution with a larger mean and a larger standard deviation. This was also valid for different features, so not just the domain length, but also in terms of the number of unique characters. So based on these insights, our goal is to detect the malicious or the what we call DGA, domains that are generated algorithmically, in the most accurate and effective manner. That's why we use these 4 main performance metrics. Now, in this case, the accuracy is considered to be a viable metric because if we go back or if we check the characteristics of the data sets, it's considered to be fairly balanced, and as such, we can use accuracy as a representative performance metric. So here we show the initial results. We see that in general, the logistic regression and SVM performed poorly, mainly because of the fact that the data is not linearly distributed, with the decision tree-based model performing the best. However, when we apply the ensemble learning model, which is basically the majority voting based, we're able to further improve the performance, particularly in terms of the accuracy and precision, and overall the F1 score, which provides a kind of weighted average of the precision and recall. Now, in order to further improve the model, we focused on trying to reduce the feature set size while not sacrificing the detection performance. That's why we proposed a ensemble feature selection model in which we choose the most representative features using different techniques and feed that to a bagging or boosting ensemble model in order to improve again the performance that might be lost due to the feature reduction. So in this case, we consider the decision trees and k-nearest neighbors as the base models for the bagging or boosting ensembles. And we consider 3 different types of feature selection algorithms, mainly based on the correlation, the information gain, or the one rule, which is more of a statistical one kind of separator for feature selection. So based on the scores given by using either correlation-based or information gain, or even the one rule, we noticed that the 3 most representative features are the length of the domain name, the number of unique letters, and the number of unique characters. And this makes sense because in general, if we change, because of the, we have more letters than numbers, we have a higher degree of freedom. That's why attackers have or they can generate more randomness when they use letters. So we use these 3 different features in order to train the models again. And we noticed that with the reduced feature set size, by effectively reducing the feature set size by more than 50%, we only sacrificed or had a slight degradation in the detection performance, which is typically only 1%. So this shows that the model is still able to detect accurately the attacks while having a significantly reduced computational complexity due to the lower feature set size. Now, the second use case, which again was a work completed in our group, was the use of ML to detect intrusions in autonomous or connected vehicles. The idea here is that we now know that more companies, car companies, are developing self-driving cars, which rely mainly on the use of sensors and communication modules installed on the car to be able to communicate among themselves or with other infrastructure in order to be able to move or route accordingly. So the idea is that these internet, or what we call Internet of Vehicles, they're able to communicate using either cellular networks or among themselves using sensors or roadside units in order to provide autonomous driving. Now, the problem is, because of this added exposure due to the communication between the sensors, with the base station, with the different infrastructure, we have new surface attacks. So these Internet of Vehicles, or these autonomous vehicles, we can divide their communication into two parts. One, which we call intra-vehicle networks, which is basically the communication between the different sensors and components within the vehicle, which is typically controlled by the CAN bus, the controller area network bus. And then we have the external vehicle networks, which is basically how the autonomous vehicle communicates with the roadside units or with other vehicles or with the base stations. So for the, as I mentioned, for the intra-vehicle or communication within the vehicle, typically the controller area network bus is used, and it's used mainly to communicate or to allow the communication between the different electronic car units. And the CAN bus is typically used because it has low cost and low complexity, and it has high reliability. However, because of its nature, it's vulnerable to several types of cyber attacks, such as broadcasting attacks and authentication attacks. So in order to, in this case here, we're showing kind of a sample denial of service attacks in which a node that's targeted can inject massive high priority empty messages into the CAN bus in order to cause latency and unavailability. So this can have a negative impact on the car, because the autonomous car cannot make decisions, for example, in terms of acceleration or braking in the required amount of time. Similarly, other types of attacks, such as the fuzzy attack, in which the node or malicious node can inject arbitrary messages with randomly spoofed identifiers, in which the result would be taking wrong decisions, or even spoofing attacks in which the node would inject messages of a certain CAN ID in order to masquerade as a legitimate user in order to take control of the target node. So here we can see kind of the danger of these intra-vehicle attacks. Similarly, because of the communication, external communication from the car, for example, for information, like to download, for example, maps, or for communication to use the wireless resources, again, we also are prone, or autonomous vehicles are also prone to different types of attacks, which are typical to regular networks, such as denial of service attacks, GPS spoofing, sniffing attacks, port scans, and whatnot. Our goal is to develop a detection module that's able to deal with both the intra-vehicle and external vehicle attacks. So the idea is to develop a machine learning-based intrusion detection system that's able to identify these different types of attacks. It can be applied to both the intra-vehicle and external network, and that can achieve a high detection rate and a low false alarm rate, and has a low computational complexity. To do that, we combine the data sets and we check if we have class imbalance, which is typically normal for network security attacks. To deal with this class imbalance, we adopted the smooth technique for oversampling, which is the synthetic minority oversampling technique. We then choose the most important features to feed to building the classification model. Again, in this case, we adopted tree-based models because they have shown to provide the best performance, particularly when it comes to network security problems. So to do that, we use two different types of data set. The first is the CAN intrusion data set from 2018, which is representative of the communication within a vehicle. And then we used the CIC-IDS 2017 data set to simulate external network data, which had many typical network attacks, such as denial of service, spoofing, sniffing, and whatnot. So by applying these different tree-based algorithms and then proposing the ensemble models, and in comparison with typical standard classification models such as KNN and SVM, we showed that the proposed classifier, ensemble classifier, was able to significantly outperform the SVM and KNN-based models, while also having typically a lower computational complexity due to the reduced feature set size. This was evident for both the Canvas dataset as well as the CIC dataset. So for both the internal vehicle attacks as well as the external vehicle attacks, we're able to detect the attacks with high accuracy and detection rate. For the final use case, which is a more generic network scenario, we know that, as you mentioned, that organizations, because they are more reliant on the internet, they've opened up the door for more potential malicious attacks. So organizations have become more concerned with their security and are allocating more resources to protect against the potential attacks or anomalous activities. So typically, some of the mechanisms deployed are firewalls, user authentication, antivirus programs, and whatnot. However, these mechanisms have not been efficient in providing complete protection for the organization networks. And that's why we need models or modules that are able to adapt as new attacks come into play. That's why we propose the use of machine learning models in order to detect or have an added layer of security. Now, our goal is to develop an intrusion detection system that's, again, computationally efficient to enable real-time or near real-time detection, as well as reducing the complexity and optimizing the IDS at different layers. So to do so, we first, again, perform normalization and oversampling to ensure that the dataset is balanced. We then implement feature selection, and then we actually optimize or train optimized machine learning models using different types of meta-heuristic and optimization models in order to have a training or a trained supervised model that's able to differentiate between normal and malicious attacks or malicious instances. So again, in this case, to prove the viability of our model, we used two well-known network security datasets, which were the CIS-IDS 2017 and the UNS-WMB dataset. You notice that the datasets are fairly imbalanced, like the ratio is almost 7-to-1, or in this case, for example, 5-to-1. So that's why we needed the oversampling techniques. First, to kind of illustrate the impact of Smoot on the training, we noticed that after applying Smoot, the number of data points needed to train a viable classifier was significantly reduced from, for example, here in this case, it was nearly around 2.5 million to roughly around 500,000 points needed for the training. Similarly, for the UNSW dataset, it was reduced from around 150,000